Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over 6K worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians, welcome to the podcast where math is figureoutable. I'm Pam Harris.
And I'm Kim Montague.
And you found a place where math is not about memorizing and mimicking, waiting to be told or shown what to do, but it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can mentor mathematicians as we co-create meaning together. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keeps students from being the mathematicians they can be.
So last week we started talking about one of our very favorite models of all time, the ratio table.
Favorite. Yep.
Yeah. And we chatted about the purpose of a ratio table as a model and how it's useful to help represent thinking as we and students navigate relationships between number. In the podcast, we described a little bit about what our ratio tables looked like and shared those to social media. So this week, as we work through some problems, we'd like to encourage you to grab a pen or a pencil and a piece of paper and practice recording yourselves. We would love it if you'd share that to social media as well. And you can record what you did to solve the problems or record the ways that we used problems to solve.
The thinking that we were using or the thinking
or
you
your
used. Yeah, y'all do it with your classes. We'd love to see your board that it ended up in doing this problem string with your students. Or if you have students that are solving problems using ratio tables and you give them some of these problems, we'd love to see their thinking. Let's start flooding social media with ratio tables. How many of you listening today have found yourself reasoning differently because of ratio tables?
Yeah.
So many people are starting to say things like, whoa, I'm looking at that completely differently now that I'm using ratio tables as a tool. So let's flood it. So like she said, grab a pen and pencil, record your thinking and post it. Let's start showing let's give everybody this inroad, this open access to the kind of thinking that mathy people do, because we can all be mathy people now that we know it's a thing.
You know what? I actually am going to say something right here that when we're looking at the strategies that people are using to solve MathStratChat problems, I find it so fascinating that I gravitate towards the ones where people did their strategy on a ratio table or with some sort of model rather than just a paragraph of words. And I don't know why that is.
Oh, I do.
I just find it so intriguing to try to make sense of what they were doing. And some people are super thoughtful about the moves that they make. And I just love looking at them.
To me, it's so much, what's the right word? Not easy. It's so much more clear. Like I don't have to sort of sift through their words. I can just see the relationships.
Yeah.
Yeah, I know ratio tables are so powerful. It's a powerful visual way to display the relationships people are using as they're reasoning through problems. Yeah, no, absolutely. Yeah.
Yeah. Okay,
So,
Pam.
Hey, before we move on from that, so if you want to get your strategy chosen to be one of ours that we highlight in a post that next week, then hint, you might want to use a ratio table. That's a good way to get it chosen. All right,
That's awesome. Okay, so today I'm going to give you some problems to solve, right?
Dun, dun, dun.
All right, and you're gonna sketch out on a ratio table how you're thinking so that we can share later what you did. Okay, cool. Yep. All right, so today I'm going to give you some problems, and I want you to think about the context of water bottles. If you had 120 water bottles. So tons of water bottles, and they came in packs of 12. How many packs would you have?
Okay, so I just am thinking about packs of 12 and water bottles.
Mhm.
And so I just spelled water with 2 T's. What is wrong with me? Water. Okay, hang on. We're gonna take a picture. No, it'll look terrible. It'll look terrible. Okay, water. I know, because I was thinking about bottles. That has 2 T's. For heaven's sakes. Tell me the numbers again. I got stuck on
120 water bottles in packs of 12.
Packs of 12. So I'm thinking about 12 water bottles in a pack.
Mhm.
So I'm going to go ahead and I wrote 1 pack to 12 water bottles.
Mhm.
And then I'm going to scale that to 120 water bottles. So times 10. So that would be 10 packs is 120 water bottles. So that 120 divided by 12 is 10.
10
Yeah.
packs. Okay.
So
Cool.
10 packs, yeah.
What if I asked you for 240 waddle bottles?
Hey, I can't spell it and you can't say it. That's excellent. So
240 water bottles.
So 240, I put in the water bottle column,
Okay.
and I'm thinking that's double 120. And so double 10 packs is 20 packs. And so I've just written times 2 from the 120 and times 2 from the 10 to the 20.
Okay, cool. What if you had 360 water bottles?
360 water bottles. So I can think of 2 ways to do this. I already have the 120 and the 240 water bottles. If I add those together, that's 360.
Mhm.
And I was kind of actually using sort of the 12 and the 24 to get 36. Like 12 tens is 120. Oh, it's a 12 packs actually. 12, I can think about it as 12 tens, but I can think about it as 12 packs as well. So 12 packs plus 24 packs is 36 packs. Wait, is that right?
Wait, no, 10
No,
packs.
that's
20
tens.
packs.
There's not
Yeah.
10. There's not 10 water bottles in a pack. There's 12
Yeah,
water bottles.
yeah.
That's where I got messed up. So I do have to think about it as 12 tens. But anyway, so thinking about the 120 and the 240 to get 360 would water bottles would mean that I would have 10 plus 20 packs, which would be 30 packs. But the other way I was thinking about it was to get from 12 to 36, I could scale times 3. And so that would be 3 packs. And then I could scale up from the 36 to the 360 times 10.
Yeah.
So that would just be another way that I could, and then that would be 3 times 10 would be 30.
Nice.
Okay. Oh, and let me tell you, I've been writing off to the side. So that problem that you gave me was 360 divided by 12, and I'm saying that it's 30. So I'm actually recording some division problems off to the side.
Oh, okay. Yeah, sometimes I do that, sometimes I don't. I don't know if there's a rhyme or reason to that. All right, next problem.
Maybe there should be. I
There
mean,
should be probably, right? All right, what if you had 1,200 water bottles?
So 1,200, I stuck in the water bottle column, and I could scale from the 12 times 100. So that would be 100. I'd scale the 1 times 100, and that would be 100 water bottles is 1,200 water bottles. Or 100 packs. 100 packs is 1,200 water bottles. Okay.
Good. 1,188 water bottles. How many packs?
1,188. So I've got that in the water bottle column. And sorry, I'm just actually writing the division problem. I forgot to write down. Okay, so 1,188 water bottles. What do I know? Well, it's really close to the 1,200. So I'm asking myself how close, and hey, it's just 12 water bottles, which is just 1 pack. It's 12 less water bottles than the 1,200, and so it's 1 pack less than the 100, so 99 packs. In other words, 1,188 divided by 12 is 99 packs.
Nice.
Okay.
All right. What about 600 water bottles? How many packs?
So I put 600 water bottles in the water bottle column, and I'm looking, what else do I know? So I can think about getting from 12 to 600. I could think about going from 120 to 600. The 360 to 600 does not make me happy. So unless I added it to the 240, that would work. So one thing I could consider would be adding the 240 to the 360 to get 600. Therefore, I'd add the 20 plus 30 to get 50. but I actually don't love that so much. I actually then kept looking, and I looked at the 1200. So 1200 water bottles was 100 packs. So if I divide the 1200 in two, I would get the 600 water bottles. So I divide the 100 in two to get 50. But now that I'm doing that, no, that's probably what I would do.
Yeah.
Yeah, that's probably what I would do.
Earlier you said something about the
No, I do have one other. Can I just throw
yeah, go
something
ahead.
else out?
Yeah, go ahead.
I'm thinking about, I didn't used to know this, but I do now. I'm thinking about 12 to 60 because you
Yeah.
said 600.
Yep.
So if I think about 12 to 60, I did not used to know that 12 times 5 was 60, but I'm kind of confirming it in my head right now because I've just already figured out that 12 to 600 was 50. So then 12 to 60 would be 5, but I could have started there. I could have said 12 times 5 is 60. So then 12 times 50 would be 600.
Nice. And that's what I was just about to ask you about. Very nice.
Damn.
What if I asked you about 576 water bottles, but this time they come in packs of 24?
Say the number again, 576?
576 water bottles, but this time they come in packs of 24.
576 divided by 24.
Mhm.
So I'm going to think about 576 divided by 12, and then I'm going to reason about how those are related. I think that's what I want to do.
Okay.
Because I've already been dividing by 12 in this whole thing. The packs had 12 water bottles. So I'm asking myself how far 576 is from that 600 we just had.
Okay.
And if I have 76, you need 24. So 576 is 24 water bottles away from 600, which is 2 packs. So that would be 48 packs. So 576 divided by 12 is 48. But you just said now you want to have the packs have 24 water bottles in it because you're asking me to think about 576 divided by 24. So if the packs have 12 water bottles and there's 48 packs, now I have packs that are twice as big. I'm going to have half as many. So I think it's 24.
Nice.
Oh, and 24 squared is 576.
Nice. So talk to me a little bit about your ratio table when the number of water bottles in a pack changed. Did you write it on the same ratio table?
I did not.
Yeah. Did you left it's almost like you had to jump off to another ratio table because the size of the packs changed. Yeah. And so then if you kept it on the same ratio table, then that wouldn't be a ratio table because then they wouldn't be equivalent. They wouldn't be proportional.
Yeah, because like right now I have 1 pack to 12 is equivalent to, in fact, if I just may, so we mentioned this last week in last week's episode that a ratio table is a table where all of the ratios are equivalent. So let me just list those. So in this particular case, the 1 to 12 is equivalent to 10 to 120, is equivalent to 12 to 240, equivalent to 30 to 360, which is equivalent to 100 to 1200, which is also equivalent to 99 to 1188. And I could keep going, but all of those ratios in all of them, there was always 1 pack to 12 water bottles until at the very end, you threw a wrench in it. Thanks a lot for that. And you said changing the size of the pack. And so now I've got 1 pack to 24. That's no longer equivalent to everything else that I have in the ratio table. So I had to get out of that ratio table to be able to think about that. But it was a super nice problem because I can use what I had there to think about it. I'm actually a little curious to go, like, what if I had just gotten that problem naked, like cold, like not without the beginning problem. So I might have been tempted to say 1 pack has 20. So I have a new ratio table, 1 pack to 24 water bottles. And then I'm asking myself, how do I get from that 24 to that 576? And I'm thinking to myself, so I'm going to talk out loud, even though I would have normally sort of done this kind of quickly. Times 10 would be 240. That's not enough. Times 2, 24 times 2 is 480. That gets me kind of close. So times 2 was 448. So times 20 would be 480. And then I'm kind of asking myself how far apart they are. And 480 to 500 is 20 plus 76 is 96. So then I'm thinking, what do I know about 96? Ooh, bam. I already had the 2 packs to 48 water bottles, and 96 is twice 48. So that must be 4 packs. And so then I can think about the 480 plus 96 is the 576. So 20 packs plus 4 packs is 24. So that's a different way of getting 24.
Yeah. I love strings like this where kids can think about relationships that they can make use of along the way. So, you use the 120 to help you with the 240 or the 1200 to help you with the 600. But I love when there's kind of a clunker at the end where you are asking, are there any relationships that you could use, or can you use the ideas that we've been tinkering with? I thought for sure that you were going to say that you were going to go back to the 1188 divided by 12, because in the very last problem, you're asking for half as many water bottles and the size of the pack is twice as much. So maybe we don't want to say quite yet. I mean, you might want to, but I just want to throw out there that there's a relationship there that might be nice to tinker with.
And you don't want to say any more than that. You want to leave that for the...
Maybe people can share with us if they see a relationship there.
So say it one more time. So you want to think about 576 divided by 24.
Yeah.
Based on what we did from 1188 divided by 12.
Yeah.
I wonder how we could ask that in a MathStratChat. I might have to think about that.
Okay.
Like how that would be interesting, right? How does this problem relate to that problem? Yeah. Cool. So let's talk about a few things that maybe are noteworthy when we use ratio tables for division, which is kind of what we just did. When you gave me the total number of water bottles in a pack, and then you said, so what if we have like a lot of water bottles, how many packs? So you're giving me number of water bottles and you're asking for the number of packs. You're giving me the total amount. We know the number in a group, and you're asking me for how many groups. And so that's one of the meanings of division. And so these were division problems, and we're using a ratio table to sort of think and reason using multiplicative relationships. What are some of the things that we think about when we use ratio tables to solve division problems? One thing you might have noticed that we just did is we did it in context.
Yeah.
And Kim and I actually had discussed, do we want to do this in context? And I said, yeah, because like, if we have anybody listening that is not adept yet with using ratio tables, then doing it in context should be very helpful. That should be, you can start to reason about what's legal to do in the ratio table. Another thing you might have noticed in both last week's episode and this one is that the tables don't have to be in sequential order. So if you looked at my table right now, it's got, I'm just going to read the number of packs. It's 1 pack, 10, 20, 30, 3, 199, 50, 5, 48. Like it's definitely not in order. And you don't have to go in order. You just have to keep the ratios equivalent. Right. When I did the 50 packs, when you gave me 1,200 water bottles and then you gave me 600 water bottles, so we had 100 packs, and then I was able to cut that in half. The first time that students do that, often they'll say, well, half the number of water bottles, so half the number of packs. And so on my ratio table, you'll see that I wrote divided by 2. And I think divided by 2 is often a way that we talk about having something. Cut it in half, we divide by 2. But eventually we're going to also want to say things like times 1/2 and make those kind of an equivalent way of thinking about that. And so as a teacher, I'm going to be kind of purposeful about doing divided by 2 first, and then start gradually introducing multiply by 1/2 to represent that, and then kind of switch up between those. What are some other things that you think about when you are thinking about ratio tables and with multiplication and division?
Well, as I was saying last week, that the purposeful time to erase really matters. So, I bet your ratio table is a little bit messy.
It is, because I'm writing in pen.
Oh, well, that's the problem. So, I think sometimes you have to be really thoughtful about when you want to erase, when it matters to keep the relationship connection that's on the ratio table there. Are kids going to come back and use that relationship again? Or is it one that you've moved on from for a short bit that you can erase and just kind of clean things up a little bit? We tend to write sometimes with arrows and sometimes with brackets.
Mm-hmm.
So when we're scaling times 10 or divided by 10, we tend to use arrows. And when we're adding or subtracting, we tend to use brackets. Just for making sense in my mind. I don't know that there's a mathematical reason to do that. You can say if you think there is.
No, yeah, it totally started when I was writing Building Powerful Numeracy. The editor asked me very nicely, thanks, Catherine. She's like, might you want to use different symbols so that the reader at a glance can tell when you're multiplying, like you said, scaling, or when you're like adding packs together, adding the number of water bottles in 2 packs plus the number of water bottles in 8 packs. Those we tend to use brackets, and it's kind of a visual way of just helping the reader or whoever's discussing, watching, looking at the model, kind of just be clear on which relationships we're using. I don't know that that's all that important, and we certainly don't demand it of students. Right. We let students, as long as students are kind of clearly notating what they're doing, times 2 versus plus this one plus that, then we don't we're not very picky about how students do that. But with teachers, I think it can kind of be helpful, and you'll recognize what I was doing in the books and on the website. And anytime you see me sort of represent things in a ratio table, then you can kind of recognize that.
I think also one other thing is that we often will see a little bit of work off to the side. So last week we described that we were doing some addition or subtraction within the problem.
Mm-hmm.
And that will be kind of like a side note, not in the midst of the ratio table, but just a kind of a little bit off to the side. Often for me, it's smaller. I don't know why. Like, side note, I'm doing this addition or subtraction also, just to continue the thinking on paper or on the board rather than try to hold stuff in my head.
Yeah, totally. One other last thing I'll mention is I've seen some teachers do a decent job of using color. That as the problems are kind of represented with one color in like the 1 to 12 or the 10 to 120 are all written in one color. But as they scale or they add the packs together, that's in a different color. It kind of helps it stand out. And then when you're, like we said, when you're done with those relationships, you kind of erase it. And so you end up with your final board, final display is really just the numbers in the ratio table, not without the scaling marks, the brackets and everything. That stuff kind of goes away. Maybe even your open number line where you're doing the off to the side addition or subtraction. That what's important is the equivalent ratios. That's sort of what stands out at the end of the ratio table. That's kind of helpful.
One last thing I want to mention this week, as we're talking about ratio tables, is sometimes people will say to us, my kids aren't familiar with ratio tables. How do I introduce them? How do I get started?
How do I teach it?
Yeah. How do I teach ratio tables? And I think the answer to that may be unsatisfying, maybe to some, because I'm just going to say you just start. So we would recommend,
or maybe scary to
right?
some.
Okay. That could be true.
Intimidating, maybe.
Yeah. So we recommend that you just start. You choose a problem string that builds a ratio table, or just ask kids what they're thinking about. And there's no formal today, boys and girls, I'm going to teach you how to write on a ratio table. We just start pulling thinking out of kids and represent it and say, hey, I'm going to represent your thinking this way. When you do that in your head, this is a way that we can represent that on paper to make sense to all of us, so we know what's going on in your head. And the kid and the student can also say, oh, when my brain does that, it could look like that. Okay. All right. When my brain does that, it could look like that. Okay. Yeah. Nice. So I ran across a quote lately. I'm actually reading a fascinating book about visionaries and some other things. And in the book, Rocket Fuel, they quote Buckminster Fuller, who I didn't really know who that was, but he was an American architect, system theorist, writer, designer, inventor, philosopher, and futurist, which I don't know what that means either. But sounds like a all-around cool guy. He invented the geodesic dome. So anyway, random. But he said a quote that I find kind of interesting that sort of plays here. He said, if you want to teach people a new way of thinking, don't bother trying to teach them. Instead, give them a tool, the use of which will lead to new ways of thinking. Nice.
May I suggest that a ratio table is that kind of tool, that if we want to teach multiplicative reasoning, really kind of a simplified version of proportional reasoning, then, and that's, we want to get people really reasoning multiplicatively and reasoning proportionally. Then it's not about, okay, like you just said, it's not about, all right, today we're going to learn the ratio table and step 1, step 2, and it's got to look like this. Instead, give them a tool, give them the ratio table, represent students' thinking, the use of which will lead to new ways of thinking. Teachers, this could be a tool that could lead to your new ways of thinking that then you can represent, or that it's then not sequentially, but as you do that, students can then be led to new ways of thinking as they use the ratio table as a tool to think with, to actually reason with. Super, super cool. All right, y'all, thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.